the reduction of order method. Reduction of order method. So what's the reduction of order method is, so what we're gonna do, we're gonna bring a second order differential equation into a first order differential equation. First order differential equation, that's the idea. So we're gonna give the result as a theorem. So the theorem is so let's say suppose y1x which is not equal to 0 is a solution of the second order differential equation which is in the standard form. Solution of the second order differential equation, that is y double prime plus px y prime plus qxy equal to 0. So this is a second order linear homogeneous differential equation. It's a second order linear homogeneous differential equation. Then what it says that then the second solution is given by y2x. So we can write this as a formula, y2x equal y1x to the integral of e to the negative px dx, divided by y1 squared x dx. So that is the formula for the reduction of order. So let's write it like that. So that's the reduction of order formula. And further, so that's interesting fact, and you can see that those two solutions are linearly independent. Furthermore, y1 and y2 are linearly independent, on any interval where y1 are not equal to 0. So on any interval where y1 not equal to 0. So if y1 not equal to 0, then those two solutions are automatically linearly independent. So this is what we call the reduction of order formula. So what we're going to do now, we're going to prove this result. The proof. So what we can do, we can assume that the second solution can be written in this form. So assume that the second solution y2 is equals to y1 times v. Okay, assume that is a solution. So we're going to make this assumption. We assume that the product y1v is a solution. So if this is a solution, now what we can do, we can take the derivatives and plug into the equation. So the first derivative is y2 prime. By the product rule, it is y1 prime v plus y1 v prime. And if you take the second derivative, and you can see that y1 double prime v plus y1 prime v prime plus y1 prime v prime plus and then y1 v double prime. So from the product rule. Now what we can do, you can see that you can combine the middle terms. So if you can combine those two, you're gonna get that y1 double prime v plus twice y1 prime v prime plus y1 v double prime. Now what we can do, we can substitute this into the differential equation. So substituting we have y2 double prime plus px y1 prime plus qx not y1 y2 prime plus qx y2. So let's see what's going to happen. So let's substitute. So y2 double prime is y1 double prime v plus 2 y1 prime v prime plus y1 v double prime, and then plus px times the second one. So you plug in the second one, you're going to get y1 prime v plus y1 v prime plus qx. We have qx, and then y2 is y1 times v. Now what we're going to do, we're going to simplify. We're going to collect the terms. So let's collect the v1 terms, y1 terms. So what are the y1 terms? There's a y1 term here, second derivative, and then we're going to go with this one, and then we're going to go with that one. So we're going to collect those three terms together. So if you do that, you're going to get y1 double prime plus px y1 prime plus qx y1. So you can see that all of them, v is a factor, we can take it out, plus then you have the rest. We have y1 v double prime plus 2 y1 prime v prime plus px y1 v prime. So we know that this is the differential equation. So we assume that this is a solution. So that means this has to be equal to 0. But at the same time, you can notice that this y1 is a solution. So since y1 is a solution, this term has to be 0 because y1 is a solution. Since y1 is a solution, this term has to be 0. So that means that term is gone. So you only get the bottom one. So we get. So we get this term, and you can see we can pull v prime out. So we're gonna get y1 v double prime plus we're gonna get 2 y1 prime plus px y1 times v prime equal to 0. So that is the differential equation we end up getting. Now the goal is how to solve this. So you can see that this is a second order differential equation, but we can reduce the degree, reduce the order by making a substitution. So that's what we call reduction of order. This is a second order differential equation, but by a simple substitution we can make this a first order differential equation. So that's the goal. So what we can do, we're gonna let v prime equal w. Okay, so that's then it's gonna be a first order differential equation. So let w equal v prime. So that's the one that makes this differential equation a first order differential equation. And then what happens if you take the derivative, we can see w prime becomes v double prime, so we can substitute, so you simply get a first order differential equation. Okay, then we can replace that, so we can substitute, so we're gonna get w prime y1 plus we have 2 y1 prime plus px y1 and then v prime, which is w, equal to 0. And you can see that this is a first order linear differential equation. Okay, so but what we can do, we can also like divide by y1. So if you divide by y1, we can write this one as w1 plus 2 y1 prime over y1 plus px times w equals 0, and you can see that this is the first order linear. First order linear. It's a first order linear. That means we can use the integrating factor method to solve it. So let's do that. So we can find the integrating factor. So the integrating factor I, which is equal to e to the p. That means that what is in the parenthesis. So it is 2 y1 prime over y1 plus px dx. So how to simplify? So this is like easy to simplify. The top one, so this is y1 prime. That means this simply becomes a natural log. So it is e 2 times ln y1 by the chain rule, because we already have the derivative of y1 prime. So that means by the chain rule you can go backward and you can write 2 ln y1 plus, here we're gonna get the integral of px dx. Now you can simplify. So if you look at the first term, this is simply y1 squared, so this becomes y1 squared and then e to the px dx. So that's the integrating factor. Now as we normally do, we can write the differential equation as a derivative. So we can write this as a derivative of w, and the integrating factor is y1 squared e to the integral of px dx. The other side is, you can see, 0. What does that mean? The derivative is 0 means the function has to be a constant. So we can write this one as w y1 squared e to the integral of px dx, which is going to be a constant. I'm going to call it c1. Now what we can do, we can solve for w. But we know that w is v1 prime. So if you substitute, we're going to get v1 v prime, which is equals to a constant e to the negative px dx divided by y1 squared. Now the next thing is, this is a derivative. To get v, what we can do, we can integrate both sides. So if you integrate both sides, so integrating, we have v, which is equals to a c1, the integral of e to the negative px dx over y1 squared x dx. So we integrate this again. and then plus c2. Now what we can do is, because we are looking for one solution, so we can make some assumptions. So what we can do, taking c1 to be 1, because you can pick any number you like. So taking c1 to be 1 and c2 to be 0, because it works for any number, so just pick 1 and 0. We have the second solution. We have the second solution, y2 x, which is simply y1 times v, but we have a formula for v now, so we can plug in. So you're going to get y1 times e to the integral of px dx over y1 squared x dx. So that's the formula. So that's the proof of the reduction of order formula. Good. Now the question is whether they are linearly independent, and you can see that if you look at a simple Wronskian, you're gonna see that they are linearly independent. So you can see to see that they are linearly independent. We can look at the Wronskian w, y1, actually y2, y1, it doesn't matter. So which is y2, y1, y2 prime, y1 prime. So let's plug in. So this is simply y2 y1 prime minus y1 y2 prime, and you can see that if you take the derivative and plug in, you're gonna get y1 prime y1, the integral of e to the negative px dx over y1 squared dx minus, so we take the derivative of y1, and then in the second one it is y1 times. So what you do is you take y2 prime. How to take the y2 prime? Y2 prime means you have to take the product rule. If you take the product rule, you're gonna get y1 prime e to the px dx over y1 squared dx, and then also you're going to get minus, we take the derivative of the second one, but it's an integral. Once you take the derivative, you get the function back, so that means you're going to get y1 squared, the you get y1 squared times whatever inside, so it is e to the negative px dx over y1 squared. You can see these two get cancelled out, so you simply get that. So that means your final would be and then also you can see that these two get cancelled out. This I think there was a small typo, so this has to be y1, this has to be y1, and then you can see that they get cancelled out. So that means you simply end up getting that term. So you're going to get negative e to the px dx. In general, this is not equal to 0, so therefore the two function has to be linearly independent by the Wronskian test. Okay, so y1 and y2 are linearly independent. That's the proof of the reduction of order formula.